My name is Mohammad Emtiyaz. It's a little complicated to pronounce, and Homeland Security doesn't like it. So, so just call me MT, okay? It's much easier. So this is joint work with Yun Ko and Matthias Seeger. We're all from EPFL. And I'll be presenting, the title is Scalable Collaborative Bayesian Preference Learning. So let me first go through explaining the title word to word. Okay, so consider a recommendation system with a set of n users, and they're potentially interested in a set of items, let's say m of them. So in a traditional recommendation setting, like a Netflix challenge, it is assumed that users express their interest about the item by explicitly rating the item. Okay, but what is more common in practice is that we might have indirect observation about users' interest in the items. Okay, so user might show her interest by clicking or buying an item more than other items, or she might just listen to some songs more than other songs. So this kind of data in the literature, it's referred to as implicit feedback data, and I'm going to call it choice of preference data in this talk. Okay, so this talk is about learning. This is good. Okay, learning users' utility from preference and choice data. Okay, so that's where this preference learning comes from. Many big names that are interested in this, and I've listed some of them here. Okay, so to learn in such recommendation system, Bayesian models have been very popular. And the Bayesian models that employ a low-rank term plus some regression terms have been extensively used in the literature. Okay, so here the low-rank, the latent factor model, which people call it, uses a low-rank product of two low-rank matrices to model the utilities. So the utilities are denoted by Z here, and the D is the latent dimensionality. So this is just like PCA. Okay. The regression models are usually just linear regression or a Gaussian process regression. Okay? So the advantage of these models is that they're robust to noise, overfitting, they can handle missing values, and they work reasonably well in practice. But not only this, that they're also useful in combining multiple sources of information. You could also quantify uncertainty with them. So if your data is sparse, then this is useful. And then you can use this uncertainty to do something like active learning, where you're presenting the user sequentially the data to learn about her utility. Okay? So this is all good. So this is the Bayesian collaborative part of the title. And the collaboration comes from this low-rank term. Okay? So this is all good when you have explicit rating in the traditional setting. But this becomes computationally challenging if you have choice data. Okay, so that's the main topic of this talk. So let me go through that a little bit. So what happens, so let's consider the latent factor model where you have only low-rank term. Okay, and let's say that the user have given some explicit rating. So there are two users and there are three items in this example. Okay, so we want to learn the utility, which is in turn learning the matrix V and U. And a popular approach is to fix one matrix and then estimate other. Okay, and then iterate between the two. So let's say that if we fix the matrix U and we want to learn the matrix V. Okay? So here, in case of explicit rating, the problem is simpler because every row of the V matrix only depend on every row of the data matrix. Okay? So I've just indicated this with these lines here. So the consequence of this is that all the rows of this V matrix can be estimated in parallel. Okay? So you get an algorithm that is linear in M. And for each row, you have to solve a system of size D, so you get this DQ. Okay, so this is quite good. But this all breaks down if the data is a comparison data. Okay, so here I've shown this. Let's say user 1 says that she likes item 1 more than item 2. The user 2 says that she likes item 2 more than item 3. Okay, so now you could see that this comparison couples the rows of the utility matrix, which in turn couples the rows of the V matrix. Okay? So all the rows are now coupled. You can't run a parallel algorithm. So you have to solve a system which is of size m times d for all the elements in this matrix. And if you do it naively, then you would pay a cubic price. Okay? But you could be more intelligent. You could do stochastic gradient. You could do coordinate descent algorithm. You could do mean field variational inference. But for us in this paper, the question that we ask is it possible, given U, is it possible to compute a closed form expression for this V matrix? So we show that it's indeed possible to compute, to get a closed form expression for this. You have to increase the memory requirement a little bit, and if you could do that, then it'll all work out. Okay? So let me give you a summary of what I'm going to present. And I'm hungry, so I will very quickly go through the steps. And there are 3 steps in which you can get scalable Bayesian collaborative preference learning. Okay, so the first step is that we model the utility, which is unobserved, by a low-rank term plus a Gaussian process regression. Okay, so this is general enough model. The second step is that we marginalize out the component of Z. So we marginalize some of the things, and we work directly with Z. And that's the key point of the paper, actually. So you'll see why this actually helps. Okay. So the second step is the key point. The third thing is, we introduce some other problems, but we design an expectation maximization algorithm to learn the matrix V, and we bring in efficiency by exploiting the fact that the data is sparse. Okay? All right, so this is not very hard to remember because I gave this talk 2 days ago in University of Iceland. And one of the professor brought his young little daughter, and she drew me this. And this is the summary slide. And she pretty much got V, U, Z, and she got my hair right, and my big shoes. So I changed my shoes for this talk. Okay, so thanks to Emma and Professor Thomas. All right, so just remember the summary, and if you don't get the details, we could talk during the poster, okay? Okay, so let me start giving heavy math by talking about the likelihood. So how do you get the data if you have the utility? Okay, so I'll be indexing throughout the talk items by I and j, users by n. Okay, so the user has provided a data where she says that I prefer item I more than item j. Now, how do we model this? We basically take the difference between the utility. Okay, so this is the utility of nth user for ith item and jth item, and we take the difference between the two. The idea is that if the difference is really positive, then the probability should be high. If the difference is really negative, then the probability should be low. Okay, so we just take the difference, we pass it through a log-a to probit link, and boom, there you go. Okay, so it's pretty simple. So now I've told you about this part. So how do we model the utility? As I said before, we have this low-rank term and a GP term. So every element in this matrix, this is ZIN, which is the preference of ith item for nth user. It's modeled as a product of these two matrices, so a row and a column comes here. And then we have this Gaussian process term. Okay, so the key point here is that we are sampling a vector of this column for every user. So this is Sn. We're sampling this independently for each user from a Gaussian process. Okay, so we take all the item metadata, we take all the item features, we form this kernel matrix, which is m by m, and then we sample each of this vector independently for each user. Okay, so there's no correlation between the user, and our hope is that this collaborative term will capture that. Okay, all right. So there are more assumptions, and this is all for computational convenience that we have to do this. So I assume that U is a random variable, follows a standard multivariate normal distribution, and I fix V and this parameter to be, this thing here to be a parameter. So my parameter set is V and sigma s squared. Now this is reasonable when your data matrix is a little bit fat. Okay, so you have more number of users than items, then it's still okay to assume your V matrix to be a parameter. Okay, and the sigma s square hyperparameter basically balances between the two terms, so the low rank term and the Gaussian process term. So if you set it to 0, then the features will have no say, and if it has a reasonable value, then you will get some benefit for cold start. problem. Okay, so that's the model. Step 1 is done. The step 2 is working with utilities directly. So now you can see that U and S, they're both Gaussian. So Z is going to be Gaussian. So I could just marginalize them out and work directly with Z. Okay? So the covariance of Z, now all the theta, the parameter, just sit in the covariance of Z, and it's a low rank term plus a kernel term. Okay? So you will see that this trick actually puts all the parameter in this latent variable, and that makes our inference, our estimation of matrix V and this parameter sigma squared easy. Okay, so that's the last step that I'm going to explain. So it's basically we're using an expectation maximization algorithm for this. So our goal, as in usual EM methods, is to maximize the marginal likelihood. So let me go through this a little bit. So here is the latent variable Z. We have marginalized out everything. All the parameters sits in the prior. Okay, so this is the prior. And then this is the likelihood, those logit likelihood that you're passing the utilities to. And then we marginalize out the latent variable. We got marginal likelihood, and we sum it over all the users, and we maximize it with respect to theta. Now, so pictorially, it looks like following, right? You have all these logit things, and then you have Gaussian. Okay, so the first problem is that the Gaussian prior is not conjugate to the likelihood, so I can't compute the posterior distribution in closed form. So I do the usual trick of Gaussian approximation. You could use a method to come up with a Gaussian approximation to this logit likelihood, and you have to compute this mean and the variance for that. Okay, and you could use Laplace approximation, variational base, but we do expectation propagation, and works quite well. Okay, so so you could do that, and let's say you get your posterior distribution. Now everything is Gaussian, so you could compute the posterior distribution. And now you want to do the usual EM trick, so you multiply and divide by the posterior, and you're going to take the log inside, invoke Jensen's inequality to get a lower bound. And the goal is to get a lower bound that is tractable, which you could maximize with respect to theta in closed form. Okay, so. So what comes next? All right. So the important thing here is that because all the parameters, and this is the most important point of the paper, actually. If you don't get anything, then you should just get this. Okay, so all the parameter is sitting in the prior. So it's in here. So I can basically ignore all the other terms. Okay? So I'm just going to take the log inside, and I'll only work with this. Okay, so that's how this looks like. I put everything else in the constant, and I have log prior. I take the expectation with respect to posterior, and this is Gaussian. This is Gaussian, so, well, you could write it in closed form like this. It turns out you only need the second moment of the posterior. Okay, so what you need to do, you use EP or some other approximation method, and you have to compute this posterior, and you have to compute the second moment. The problem is not solved yet, right? So let's say, I haven't told you how to compute this, this summation, but let's say that if you could do that, then it turns out that the problem is quite simple. Well, this is the objective function again. I use the fact that the covariance matrix has this low rank plus a kernel matrix form. Okay? And if you go and read the classical paper, probabilistic PCA, and you have to do some math here, just take the Cholesky of that, push it in there, and you do all that, and turns out that the maximization with respect to V and sigma square, you could obtain that just by taking an eigenvalue decomposition of the sufficient statistics. Okay, so that's the key point. I'm skipping all the details, but basically, if you could accumulate this matrix, then you just have to do an eigenvalue decomposition. And in paper, we show that this eigenvalue decomposition, it's not going to be m cubed. It could be reduced to m squared d because there is some structure in the matrix here. Okay, so the details are in the paper for this. Okay, so we don't have a cubic scaling now. It's quadratic. At least it's it's not that good, but it's still better. Okay, so the next question is that can we actually do this? And at first, you might think that the problem is solved, but it's not, right? Well, I don't think any. Okay, so let me tell you what the problem is. Well, this matrix is huge. It's of the order of a number of movies, right? So it's a big m by m matrix, and you have to compute it for all users, right? So this is just not practical at all. Okay, so there is a trick in the paper. Well, what we do is basically we just use Woodbury formulas. It's really, really simple. And we use the fact that every user has rated only few movies. Okay, so we have only few pairs. Okay, so let's say that EP parameters, you get some of them which comes from so this will be, the length of this will be equal to the number of pairs that user has compared. Okay, so the covariance, which can be used to compute this, can be written as prior plus something that comes from the likelihood. Okay, and you basically just use matrix inversion lemma or Woodbury identity to express this inversion in terms of these small matrices. So basically, what you do, you compute these small matrices only, and you never do this multiplication. You have to compute this sum. You could push this sum inside, and you could accumulate these small matrices only. So that's the idea. So you compute these small matrices. So maybe user has rated or compared only 5 movies. So your matrix is 5 by 5. You compute it for that user. You add it to big M square matrix, and you keep doing that for all user. And you could do all this in parallel. So how does the overall algorithm looks like? Well, here it is. The first line is the most expensive one, and I'm really sorry for that. But there are tricks that you could do to get rid of this problem. But you have to compute the Cholesky of the kernel matrix first. But you have to only do it once if you fix the kernel matrix. Then you initialize your parameter. And then for all user in parallel, you do EP or any other method to compute these small matrices, so these sufficient matrices. So if Pn is the number of pairs that user has provided, then this is going to be cubic in that. Okay, so you do a lot of little matrix inversion, and you add it to a big matrix S, and then you do eigenvalue decomposition. The details are in the paper, and you could compute both of these parameters. Okay. So basically, the computation cost is the most here, is m squared d, and the memory cost is to accumulate this matrix, which is m squared. Okay, so as compared to the naive method, we have lower cost, and everything is in closed form, so it might be useful for some application. Okay. All right, so let's go to some results, and I'm going to tell you that, yeah, my paper is great, my method works amazing. You could see that in the paper. But I think the more insightful result that I want to present is this, and the table is a little bit, it's going to take more time, so I'm just going to skip the table. Just going to give you the summary. Basically, the summary is that if you use only GP term, then it performs worse than using the collaborative term. So the collaborative term is really, really powerful. And people have seen this during Netflix challenge, actually. Okay. So the collaborative term is very powerful. When you put the both terms together, where they're performing almost equal to the collaborative term, but then the GP term helps the user who don't have much data. Okay. So the features actually help the cold start problem. Okay. So that's one of the insight that we got here. And this table is in the paper. Okay. Here's some visualization for movie lengths, 10 million data. There are around 10,000 items, 45,000 users. And I'm showing you the matrix, the V matrix, and I have rotated it here. So this is basically the rows of V matrix. So these are movies. And I'm showing you around 7 factors here. And you could see some clustering here already, right? So yeah, turns out that this clustering is just the genre of the movie. And the method seems to find this clustering automatically. Okay. Okay, so runtime comparison on movie lengths, 10 million. What I'm showing you here is different number of training pairs that you could change, and on a single machine, the E step is increasing, because you have to do this cubic computation. So it's increasing polynomially as you increase the number of pair, but the M step almost remains the same. So it's just you form this matrix and you do an eigenvalue decomposition, and that's all it is. So you could reduce this E step computation by employing more computers, because you could parallelize everything. And when you do that with 32 machine, we get around 6 times speed up. Okay. All right. So it's the last thing, and I have a minute, so I'll go very quickly over this. And this is I'm trying to demonstrate how these models are useful for quantifying uncertainty. X-axis here you could think of as a person's spending more and more time on Netflix and watching more and more movie. And let's say that this person is a person who likes comedy movies, and she's somehow giving you this feedback that she likes comedy movies more than drama and more than action. But she never says anything about whether she prefers drama more than action or not. Okay? So she's only giving you data about that she likes comedy, because perhaps she always clicks on the comedy movies. Okay, so as the time goes by, the method becomes more and more confident. So this is probability of how much she likes comedy, how much she prefers comedy over other, and becomes more and more confident. But for other two categories, the probability remains very neutral, as we would expect a method to be. So it's around 0.5, and you're not sure if she likes comedy or not. Okay, so it's quite robust to quantify uncertainty. So you can do the same thing with action. Okay. All right, so let me summarize what I've just presented to you. I talked about learning utilities from implicit feedback data, preference and choice data. And I showed you how this choice data introduces couplings within the rows of the utilities. And there is a computational difficulty that arises because of this. And I showed you that by doing some clever reformulation of the problem, you could still reduce the computational complexity and get a closed form solution. Okay, so I'll skip the future work. Thank you.
So are there any questions? So there's a question on this side.
Thank you for the talk, Emtiyaz. Maybe I missed this or I did not understand it clearly. But on slide 11, you do the Cholesky decomposition, right?
Slide 11.
Yeah.
Okay.
Right there at the first point, right? Do you need to do the full Cholesky for this one?
Yeah, unfortunately, we have to.
Okay.
But you could do a lot of approximation. The problem, this problem arises because of this step. Right? So we were very desperate to get a closed form solution. So, you know, when you want to apply PPCA to this objective function, basically it works when this K is an identity.
I see.
Right? So we're doing Cholesky and we're pushing that in there. You could do an approximation. You could do, let's say, eigenvalue decomposition of that, and you could just do a approximate one. And I think that should work too.
Thank you.
Yeah.
All right, are there any other questions? I guess people are shy right before lunch. Well, let's thank all the speakers from the session again.